Okay, this is some AP calculus exam preparation questions. And the important thing about walking through these questions is getting to know how they ask the questions on the AP exam, because at first glance they can be a little bewildering because it doesn't seem like it's the same kind of questions that you've been doing in a textbook or in class and so on. So it's really important just to see that they really are the same thing. They just might be phrased a little different, and so that's why the practice is so important here, is to see the type of questions that are on there. So let's just hop into a couple examples, and these are no calculator questions. So when you see those, the numbers should be a little more under control than what you would see in normal calculus questions. So no calculator questions are kind of nice actually, because they things don't get completely out of hand. Well, let's dive right in here. There's a table here, and it says hot water is dripping through a coffee maker, filling a large cup of coffee. The amount of coffee in the cup at time 0 to 6 is given by differential function c, where t is measured in minutes. Selected values of c at t measured in ounces are given in the table above. So what this table is telling me is they've measured how many ounces are in the cup at certain times, at 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, and 6 minutes. So just a table of values here. It says use the data in the table to approximate C prime at 3.5. Show the computations that led to your answer and indicate units and measures. So they're laying it all out for you, what you're trying to accomplish. But this question can be very surprising because it doesn't look a lot like other questions. Oftentimes when they ask for the derivative at a certain value, they give you the equation. Here they haven't given you the equation. They've gone back to a table of values. Now, and even worse, C prime at 3.5. 3.5 doesn't even appear on the table, and that can catch you off guard too. But actually, 3.5 is what you probably really want here, because if you want to find the instantaneous rate of change at 3.5, we don't have a lot of information here, but we do have the amount in the cup at 3 seconds and the amount in the cup at 4 seconds. 4 minutes, 3 minutes and 4 minutes. So we could find the average rate of change between 3 minutes and 4 minutes, and that's going to be our best way to approximate. See, that's the important word here in all this, is that said approximate. So if we find that average rate of change from 3 to 4, and you say, well, why 3 to 4? Why not 2 to 5 or 1 to 6 or 2 to 5? There's lots of other options here. Well, because 3 and 4 are the closest possible numbers. And going back to the roots of derivatives, we always want to get as close as possible. We can't get that close because we don't have the equation here in this particular situation, but as close as we can get, we can approximate using 3 to 4. So my approximation of C prime at 3.5, and I'm going to use equals, and I'm going to put a little dot here. Sometimes people use little wavy lines for the equal sign to say approximately. This isn't the exact value, is I'm just going to find the amount of coffee at 4 minutes and subtract the amount of coffee at 3 minutes over 4 minus 3. Just actually find that average rate of change from 3 to 4 and use that as my approximation. So what do I get? I get 12.8 minus 11.2 over 1. And the fact that it's over 1, this is what non-calculator questions are often like, is that the numbers are very controlled here. So what I get here is 1.6, and it says include the units. So this is going to be 1.6 ounces per minute. And let me just check, did I show all my steps? Yes, I did. So I'm going to go C prime at 3.5, and then I'm going to put equals approximately there again at the end. Okay. So then it says, is there a time between 2 and 4 that C prime at 2 equals 2? Justify your answer. So it says between 2 and 4. So before I get started on knowing whether it's going to be, whether C prime at 2, whether there's going to be a time when it's C prime is equal to 2, let me find that average rate of change from 2 to 4. So what I'm going to do is find average rate of change from 2 to 4. So that's amount of coffee at 4 minus amount of coffee at 2. All those C's and those brackets are messing me up a little bit there. Okay, so coffee at 4 was, I think I see 12.8. Minus coffee at 2 is 8.8 over 2. And what I get is 4 over 2, which is 2. And that's interesting because the average rate of change over that time period is 2. And this goes right back to the mean value theorem. And the mean value theorem states that if the average rate of change from 2 to 4 is 2, then somewhere in there, the instantaneous rate of change was also 2. It might have been there a lot of times. It might have been there the whole time. But somewhere in there it had to hit 2 because the average rate of change over that section was 2. Now, don't forget the mean value theorem had an important little preamble to it, is that the function had to be differentiable and continuous. So if it's differentiable, it must be continuous. So this does fit the restrictions of the mean value theorem. So I'm ready for my conclusion. Therefore, due to the mean value theorem, I'm not going to use the short form here, I'll write it out here. Due to the mean value theorem, C prime at t must equal to somewhere in the indicated domain. Okay. So another one of those questions. It doesn't really talk about the mean value theorem. You got to kind of reach out and grab that mean value theorem from your base knowledge there. Okay, next one. Use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1/6, 0 to 6, c at t dt. Using correct units, explain the meaning of this integral. Well, you know what? I'll leave the 1/6 out there, and hopefully when you see the 1/6, you sort of know what's going on here with the 1/6. But if you don't, that's okay. We'll talk about it at the end. I want to deal with that integral first. So, and sometimes setting up these sections for the Riemann sums that go on here, it can be a little awkward. So let me go through all the steps that we're talking about here. Is to find out how wide each of these rectangles that we're going to do is, what I do is I go b minus a over n. And then this can be obvious. If you've done enough of these, or if you're practiced at them, maybe you don't need all these steps, but we're talking about an interval that goes from 6 minus 0, and they want 3 intervals. So I get my delta t of 2. That means each of the intervals I want to do is 2 wide. Now, if you're really good at these, you don't need this little diagram here, but the little diagram can be very helpful, and the diagram just goes, okay, so my interval goals go from 0 to 2, from 2 to 4, and from 4 to 6. Yes, that matches up with 3 intervals. And so then what I'm looking for is rectangles. And, well, okay, I'm just going to peek here so I can draw my rectangles for so I see that at 1, it's 5.3, then 11.2, and 13.8. If you're not sure I'm getting those numbers, I'll show you that in just a second. But I just use that to sort of get to scale rectangles, even though you don't really need to scale rectangles. You don't need the rectangles the right sizes to find these areas, but I did it anyways. And so what they said, use 3 indicated by the data to approximate, use a midpoint sum. So I'm going to use the values at 1, 3, and 5. So that's MRAM that they're asking for there, is to find the area of these rectangles using the middle value. So what I'm doing is I'm saying, okay, to find 1/6, and I'm just doing the integral 0 to 6, c at t dt, what I'm doing is going, okay, 1/6, here's the actual integral inside. Is each of those rectangles is 2 wide, so it's width 2 times the height, and then plus another width 2 times the height, plus another width 2 times the height. And I like writing it out like that, where I put all the widths in there to remind myself I'm just finding the area of 3 rectangles here. And so each rectangle has base 2, and I just need the heights. So I need to know what was the value at 1, and the value at 1 was 5.3, so I'll put that in there. And the value at 3 was 11.2. And the value at 5 was 13.8. So I knew I was using 1, 3, and 5, and that's how I knew to draw the rectangles sort of the sizes I did, even though that doesn't matter at all. I only did that so you could really see what we were up to with the rectangles here, just sort of a teaching thing there. And so what I get when I punch that all into my calculator is I get that integral is worth 60.6. Still got to be divided by that 6 out front. And so what I get here is 10.1. Now, what does that represent? Now, you might be able to just look at the numbers at the table and sort of get a feeling for what it represents. But this 1/6 out front is sort of supposed to trigger us to remember that average value is 1 over b minus a times the integral in question. So this was an average value that this was calculating. And the units help with that. C at t dt was finding the average, the value of cost times time, and then I was dividing by the 6, which is the time. So we get back, not cost, volume there, that the ounces there. So this is 10.1 ounces, which is the average coffee in the cup. Yeah, that's what we're finding there. And then finally, in the last question, back to something a little more what we're used to. Actually, D's the hardest question to do, but we did so many of them in regular calculus that we think that's the easy one. It says the amount of coffee in the cup is modeled by, and here's the equation finally for the situation. Using this model, find the rate at which the coffee is changing when t equals 5. So what I've got at b at t equals 16 minus 16 e to the negative 0.4t, and then I'm just finding the derivative here. Derivative of 16 is 0, so the derivative of this part is, okay, so the derivative of negative 16 e to the negative 0.4t is negative 16 e to the negative 0.4t, and then multiply that by the derivative of the inside, which is the exponent there, and so what I get is 6.4 e to the negative 0.4t. There's b prime at t. They want b prime at 5. So I'm going 6.4 e to the negative 0.4 times 5. And so it's 6.4 e to the negative 2, which I'm going to, with a non-calculator question like this, I'm just going to leave that at 6.4 over e squared. And that's ounces per minute. Therefore, the rate at t equals 5 is 6.4 over e squared ounces per minute. A little therefore statement there. Okay, that's a little more traditional type calculus question. The other ones are really reaching to see, not only do you know the calculus, but do you really know what's going on and why we're applying the things we do there. So, okay, that's the first example. Example 2. Back to over to some integrals instead of some differentiation. It says f at x equal 2x squared minus 6x plus 4, and g at x equals 4 cos 1/4 pi x. Let R be the region bounded by the graphs f and g as shown below. Find the area. Actually, a fairly traditional area question here. The only thing you sort of have to decide is which one's the upper and which one's the lower. And I need to tell you, if you get it wrong in an upper lower question like this, all that'll happen is you'll get a negative answer and you'll know you've done it the wrong way around. But I know what cosine sort of looks like, and cosine sort of level at 0 there. So this one's the g at x, the cosine graph, and then this must be the f at x there. So again, I don't want to overstate how not much of a problem this whole positive negative thing is, because if you get it wrong, you just do it the other way around. I do also want to mention that you could grab your you could sub in some convenient values, like sub in like what would be good here. That's pi over 4 inside there, so you could sub in like a 2, and sub in a 2 to here and see which one's bigger, because subbing in 2 into both of those is pretty easy, because what I get is pi over 2 in there, and in your head you can do cos pi over 2, which is 0, and that would help. Okay, so 2's too far over, so maybe 1 would work. Okay, so not 2, 2's too far over here, so we're going to do 1. We'd sub in 1, which is sort of halfway in between, and that would come out to cos pi over 4, which cos pi over 4 is right in a special triangle, and subbing in 1's there. So no big deal here is finding which one's the upper and which one's the lower. So if I want to do this area, I'm going area equals integral from 0 to 2, upper minus lower. Okay, so upper is 4 cos 1/4 pi x minus 2x squared minus 6x plus 4. Oh boy, be careful with negatives. I don't know. That's got to be one of the top errors out there in integrals like this, is forgetting to subtract here all those terms, and so you don't get the subtract and negative. So I'm going to just simplify that up a little bit. 0 to 2, this is no problem. 4 cos 1/4 pi x, and then that's negative 2x squared, positive 6x minus 4. Easy to make a little mistake there. And then the little anti-differentiation here. So what do I get? 4 cos, so I guess I would have had a sine to start with. 1/4 pi x. It's going to be a pi over 4 that pops out of there, so I need a 4 over pi ready for it, but there's already a 4 there, so I think a 16 over pi. Maybe you've got your own method of how to handle that. I just sort of play around with the coefficients until I get it right. And then what's this? Minus 1/3 x cubed plus 3x squared minus, well, I don't like that, minus 4x. This needs a nice square bracket. Evaluated between 0 and 2. And it looks a little scary because you got to sub in 2 and 0. But again, because it's not a calculator question, they've probably set it up in a way that things work out nice. So my first bracket is 16 over pi. And if I'm subbing in x equals 2, I get sine pi over 2, which makes me feel a lot better because in just a second I'll be able to evaluate sine pi over 2. And then that's minus 8/3. And then that's like a 12, and then that's like an 8. That's the first bracket. And look what happens when you put 0 into the second bracket. Sine of 0 is 0, minus 0 plus 0 minus 0. You know, this is what calculator questions are like sometimes, is, you know, you're going to have a lot of easy stuff in there. And so 16 over pi, sine of pi over 2 is 1, so that stays the way it is. Ooh, a little common denominator work here. 36/3 minus 24/3, something like that. Just double check those in my head. Yeah. And then so I get 16 over pi, and that'd be plus about 4/3. Not about 4/3. Oh, maybe minus 4/3. Hey, I'm getting carried away trying to do a conclusion here. Better check that. Minus 32 plus 4/3. Yes? That's what I'm after. There's plus 4/3. Okay, so don't let questions like this, when they come along that are a little more straightforward, I think, a little more traditional question there. When you get those, please be careful to not mess up negatives and so on. Really be careful with those as you're going along there. Okay. Next, write but do not evaluate an integral expression that gives the volume of a solid generated when r is rotated around the line y equals 4. Now, a lot of the rotations that regular rotations you see will be rotated around the x-axis. This one's rotated along the line y equals 4, which isn't a big problem. It's still just a washer question. And so here's the, let me just get the formula for washers there. Integral from 0 to 2. I guess I could put the pi out there. R squared minus r squared over from dx along dx there. And so the radius here, so this radius here, the outer radius will be that distance there, while the inner radius will be that distance there. So you've got to do some thinking here, is that outer radius, which is the one that gets farther from the line y equals 4, is down to that f at x function there. And so that radius is going to be pi 0 to 2. Let's just get that radius in there. Oh, maybe a second set of brackets will be good here. So this is the big R. The big R is 4 minus that f, which is 2x squared minus 6x plus 4. And that's all squared. So that's the radius of the outer. And then the inner one is going to be, it's again 4 minus something, but 4 minus the g at x, which is 4 minus that 4 cos quarter pi x. And, ooh, better do some counting on my brackets here. Squared, that closes that circular brackets, and then dx. And it says write but do not evaluate, but maybe I can do a little better here. Pi integral 0 to 2, tidy up that bracket. So 4, there's a minus 4 in there, so negative 2x squared minus 6x all squared. Oh, that needs a square bracket. That's the big R squared. And then, oh, hang on. On that line, I didn't need that pi. I common factored that pi up front, so I didn't need that pi there. And then in this one, minus, well, nothing I can do in there. So 4 minus 4, nothing really productive anyways. You might feel like you want to common factor the 4 out or something like that, but I don't think that's hugely productive here. And they said write but don't evaluate. So that's the crazy integral I get there. And with the squareds in there, this would be a nasty integral to evaluate. If they did ask me to evaluate that on the AP Calculus exam, it would be a question where you're using your calculator, okay? C. Oh, last one. Okay, C. The region R is the base of a solid. So apparently there's some solid. This R is, and it comes straight up out of there, kind of a weird looking a snail type base shape coming out there, you know, some kind of weird bookend, or I don't know what they'd use that for. But and for this solid, each cross section perpendicular to the x-axis. So let me switch colors so you can see what I mean. Each cross section perpendicular to the x-axis. So something like this. That right there is the cross section perpendicular to the x-axis, and that's the base of a square. So that comes straight up out of the page there as the base of a square. And I like these ones because squares are really simple to deal with. Write but do not evaluate the integral expression. So I'm just going to go base of that square. It will be equal to, the top minus the bottom here, basically. And so that base of that square is going to be 4 cos, I wrote it enough times, but 1/4 pi x. That's the upper. And then the lower is the 2x squared minus 6x plus 4. Was it plus 4? Yeah, plus 4. So I'll simplify that down now while things aren't too crazy symbol-wise. And so that's 4 cos 1/4 pi x minus 2x squared plus 6x minus 4. That's the base of the square. So if I want to find the volume of that, I want to add up all those squares, I'd be going volume equals integral from 0 to 2, this base of the square, which is 4 cos 1/4 pi x minus 2x squared plus 6x minus 4, and that's all going to be squared because it's the base of a square. So the area of that square every time would be the base squared. Maybe an extra step in here. The volume of these shapes is always integral of area dx, and that's always what you're doing to find these volumes, is you're finding the integral of the area across the dx's there. Okay, so the idea being is that we've focused on two types of questions you might run into: table of values, and one of these questions that's areas that has a washer in it and a regular integral in it as well. And sometimes you just have to write the expression for the integral but not actually evaluate it. And in the next video, I'll go through some ones where you have to use your calculator to evaluate. The idea being now is there's some questions from another year, 2 assigned questions, where you can try these, try this whole thing out and do it yourself there, and try and find, do some questions that are very, very similar. So there's just 2 questions there for assigned work to try out those concepts, and then maybe go search for the questions like that on previous exams or in your 5 steps to a 5 type questions. Now, if you check online, there's nice answers and scoring guides to show you how they score these questions. So you can try out those questions and then check your answers and see if you got the correct answers. One little correction here I wanted to do on an earlier question is that 4/3 in my mind was a minus 4/3, and that was right because I lost a subtraction somewhere along the way there. So it was 16 over pi over here, and that was supposed to be a minus 4/3. One of the signs I got wrong there. Let me just see if I can find it real quick there. Right there, negative, positive. Oh, it was in the integral back here. So when I did this 2x squared, this was supposed to be a negative 2/3 x cubed instead of a just 1/3. Maybe you saw that as you were watching the video there, that mistake was there. So let me just fix that up there. That's going to be a minus 16/3. And that's going to be a minus 16/3. And so then I get the negative 4/3. Okay. And I noticed that mistake. I knew it was supposed to be subtract 4/3 there. Okay, so try out those assigned questions and then compare your answers with them and get used to the scoring guide so you see how they score questions like those. And then search out on previous exams or in 5 Steps to a 5 other questions like those so that you get used to those. So you're not surprised when you get those type of questions and you have those down pat. And then move on to the next video and where we go after some different types of questions. Okay, have a great day.